Welcome to Sleepy Scientist Stories. Tonight, from wherever you are watching this, we drift into the most unsettling corner of quantum mechanics. What if every atom in your body, every breath you take, every flicker of consciousness dancing through your mind right now is nothing more than information processing in an infinite cosmic simulation? As you settle into the quiet of this moment, physicists around the world are grappling with a paradox so profound it shakes the very foundation of existence itself. The quantum realm whispers of a reality that dissolves under observation, where particles exist in impossible states until the very act of looking forces them to choose. Could it be that what you call reality is merely the universe's most elaborate magic trick, a convincing illusion woven from probability waves and quantum uncertainties? Tonight, as your thoughts begin to slow and your breathing deepens, prepare to journey into the heart of a mystery that suggests everything you've ever known might be far stranger than dreams. What if reality itself is not smooth, but woven? What if space and time, which appear endless and seamless to human eyes, are in truth stitched from threads so fine that no microscope can see them, no hand can touch them? At the quiet edge of modern physics lies this unsettling truth. The universe may not be a continuous canvas, but a fabric of discrete quanta, the smallest grains of existence. Quantum mechanics first revealed this hidden structure, showing that beneath familiar forms nothing is truly solid. Particles are not tiny marbles spinning through the void. They are ripples of probability, flickering in and out of being. They emerge as matter only when measured, as though the cosmos waits to be asked before it answers. An electron circling an atom does not follow a tidy orbit like a planet around the sun. Instead, it hovers in clouds of uncertainty, present everywhere and nowhere until forced into place by observation. Even time, which feels like an arrow flowing forward without pause, may not be continuous. Physicists speculate that at the smallest scales, the Planck time, unimaginably brief, moments may tick like beads on a string, discrete and countable. Likewise, space itself may be quantized, divided into irreducible units smaller than any known particle. The smooth surface of reality is like a painted canvas. When examined closely enough, it dissolves into brushstrokes, textures, and gaps. This idea transforms the world around us. A mountain, appearing steady and eternal, is in truth a restless congregation of atoms, each trembling in ceaseless motion. A stone resting on the ground hides within it quantum uncertainty, particles tunneling through barriers, fleeting energies that cannot be stilled. What seems solid to the hand is instead a storm disguised as stillness, an ocean of fluctuations disguised as form. Physics did not arrive at this vision lightly. Experiments with light and matter, scattering, photons and electrons through narrow slits, revealed interference patterns that could not be explained by classical rules. The behavior of the tiniest entities resisted prediction, offering instead only probabilities. Yet the very equations that describe this strangeness turned out to be among the most accurate tools ever created. Within their abstract symbols lies the blueprint of lasers, semiconductors, and even the devices through which such stories are told. The paradox is clear. Uncertainty is not weakness, but foundation. From this foundation rises a meditation. If everything is built upon flickering possibilities, then reality itself is a fragile balance between chance and form. The ground beneath existence is not bedrock, but shifting fabric. And yet, it holds. The chair supports, the star shines, the atom endures. Physics shows that stability emerges not despite uncertainty, but because of it. Order rising from quantum chaos, harmony born from fluctuations. This is where the journey begins, at the quiet realization that the everyday world rests on invisible grains of possibility. From here, the path leads toward deeper mysteries, entanglements that stretch across galaxies, paradoxes that blur observation with creation, and questions that whisper whether what is seen as real might only be the shadow of something stranger. The fabric is not finished. It unravels into the unknown, inviting us to follow. Light has always carried mystery. For centuries it was seen as a wave, rippling through space like sound through air or water. Then experiments suggested it could also behave as particles, tiny quanta of energy called photons. Neither picture alone could capture its full nature. Sometimes light diffracts and bends, spreading in interference patterns. Other times it collides like a bullet, knocking electrons free from metals in the photoelectric effect. Light does not belong fully to either description. It moves between identities, wave and particle both, refusing to be bound by human categories. The most haunting demonstration of this truth came through the double-slit experiment. A beam of photons passed through two narrow slits, forming a pattern of alternating light and dark bands on a screen, just as rippling waves would. Yet when detectors were placed to measure which slit each photon travelled through, the pattern vanished. The photons behaved as particles instead, taking one path or the other. In observing them, the experiment altered them. The act of measurement seemed to rewrite the story light was telling. This paradox stretches far beyond physics laboratories. It unsettles the idea that the universe has definite properties independent of observation. If light can shift its behavior based on how it is examined, then reality itself may not be a fixed stage waiting in silence. Instead, it may unfold differently depending on interaction, shifting like a script that changes with its audience. Such behavior suggests that the smallest elements of existence remain fluid until engaged, balancing between possibilities rather than committing to one. The lesson of the double-slit experiment is not confined to photons alone. Electrons, atoms, even molecules display the same duality under careful tests. Entire systems can rest in multiple states at once, superpositions of potential that only collapse into certainty when measured. The everyday world of solid objects hides this strangeness because superpositions blur into stability at larger scales. Yet the principle remains. At its foundations, reality is written in probabilities, not absolutes. In this view, observation is no longer passive. It is not like standing at a distance to watch a scene unfold. Instead, observation enters the stage, shaping the very events being studied. The boundary between observer and observed blurs, leaving unanswered questions about where the line truly lies. Is it in the instrument that detects a photon, or further up the chain, in the mind that interprets the result? The paradox does not resolve easily, and perhaps it is not meant to. The double life of light is more than a puzzle of physics. It is a mirror, reflecting how limited perspectives can never capture the whole. Light is not wave or particle, but both, depending on the frame through which it is seen. This truth opens a wider doorway, one that leads into deeper mysteries of entanglement, uncertainty, and the strange role of the observer. The path winds onward into a universe that is less fixed than it seems, where possibility is the foundation upon which reality quietly rests. In the quiet fabric of physics, there exists a phenomenon so strange it unsettled even Einstein himself. He called it spooky action at a distance, a phrase that carried both skepticism and awe. It describes entanglement, the moment when two particles, once linked, continue to share a single state, no matter how far they travel apart. Measure one, and the other is instantly defined, as though the separation between them had dissolved into nothing. This is not speculation, but experiment. Over decades, physicists have tested entanglement with photons, electrons, and even atoms separated by vast distances. Time and again, the results are the same. The particles remain connected, their properties correlated beyond what chance or hidden instructions can explain. No signal passes between them, no exchange that travels at the speed of light. Instead, they behave as if distance does not exist. The universe at this level seems less like empty space dividing objects, and more like a web where all points touch. The implications reach far beyond the laboratory. Entanglement suggests that the division between here and there, between near and far, may be illusions of scale. Locality, the idea that events are bound to their positions in space and time, breaks down at the quantum level. What happens in one corner of the universe can be reflected instantly in another, as though reality itself is stitched together by invisible threads. This is not the world of classical physics, where cause travels like ripples through a pond. It is a universe where the pond itself may be one indivisible whole. The image is unsettling but also profoundly unifying. If entangled particles are bound no matter the gulf between them, then perhaps the cosmos itself is less a collection of separate objects and more a single, continuous tapestry. Each galaxy, each star, each atom may be woven into this fabric, not isolated, but participating in a larger whole. Entanglement becomes not just a paradox, but a whisper of connection. That separation is surface, and unity lies underneath. Scientists continue to push entanglement into new experiments, linking ever larger systems, sending entangled photons across satellites in orbit, testing whether the phenomenon can scale. Already it fuels technologies once thought impossible. Quantum communication, unbreakable encryption, even the foundations of quantum computers. What began as a philosophical puzzle is now shaping the tools of the future, proof that mystery and utility can coexist. And yet, the paradox remains unsolved. How does entanglement work? Why should two particles separated by light years behave as one? The equations describe it with precision, but the meaning remains elusive. Perhaps the answer lies not in the particles themselves, but in the fabric that holds them, a deeper layer of reality where distance and time are not fundamental, but emergent. Entanglement shows that the world is not divided, as it appears. It reminds that every particle, every breath, every star is bound in unseen ways. The cosmos may look like countless points scattered across darkness, but entanglement whispers that it is whole, a unity dressed as multiplicity, a single song played across instruments scattered through the void. In the language of quantum physics, the world is not built on certainties, but on possibilities. An electron does not sit at one precise point until measured. A photon does not travel along a single path until detected. Instead, they exist in superpositions, clouds of probability, each containing every potential outcome. Only when observation occurs does the haze of possibilities condense into one reality. This transformation is known as the collapse of the wave function, and it suggests that the very act of observing is inseparable from the unfolding of existence. This notion unsettles the classical view of nature. In older physics, the universe marched forward like a machine, indifferent to whether anyone was watching. Objects had definite properties at all times, regardless of measurement. But quantum mechanics breaks that certainty. When a particle is left unobserved, it behaves like a wave of possibilities. When it is measured, it solidifies into a single state. The act of observation is no longer passive. It is active, like a stone dropped into still water, reshaping the ripples of the pond. The question then arises, what qualifies as an observation? Does the presence of a detector suffice? Does the interaction of matter itself collapse possibilities into facts? Or is awareness, consciousness, required to turn potential into reality? Physicists are divided. Some argue that measurement is purely physical, no different from one particle striking another. Others, more cautiously, wonder whether mind plays a deeper role, not as a passive witness, but as a co-creator of what is real. The debate remains unresolved, an open wound at the heart of modern science. Experiments have only sharpened the paradox. In variations of the double-slit experiment, choices about whether to measure seem to alter results even retroactively, as though the universe adjusts its story to fit the act of observation. This has led some to suggest that the observer is not outside reality but entwined with it, woven into the same fabric as the particles being measured. If so, then the universe may not have definite form until something, or someone, looks upon it. The implications are profound. If observation shapes reality, then independence dissolves. The world is not simply out there, waiting in fixed form, but emerges through interaction. Each measurement becomes a moment of creation, a narrowing of infinite possibilities into one path. Reality may be less a stage upon which events unfold, and more a script written anew with each act of observation. And yet, the mystery is not meant to be reduced to mysticism. Quantum theory does not prove that consciousness creates the cosmos, only that the boundary between observer and observed is more blurred than once believed. Whether detectors alone suffice or human awareness is essential, the paradox remains. Without observation, there is no fact, only possibility. In this uncertainty, the shadow of the observer grows long. It suggests that reality may not exist independently in the way common sense insists. Instead, it may be participatory, arising from the interplay between potential and perception. As the journey continues, this paradox deepens, leading toward Schrödinger's box, where life and death themselves are suspended until the lid is lifted. In the early days of quantum theory, even its founders struggled with the unsettling consequences of its equations. To capture their strangeness, Erwin Schrödinger devised a thought experiment in 1935, one that remains famous to this day. He asked us to imagine a cat, sealed in a closed box. Inside, a small device contains a radioactive atom, a detector, and a vial of poison. If the atom decays, an inherently quantum event governed by probability, the detector triggers, shattering the vial, and the cat dies. If the atom does not decay, the cat survives. Yet until the box is opened, until observation occurs, quantum theory insists the atom is both decayed and undecayed. The cat, tied to this fate, becomes both alive and dead at the same time. This image is absurd at the level of daily life, where creatures are either living or not, never both. But in the quantum world, such paradoxes are not mere imagination. Superposition, the ability of a system to exist in multiple states at once, has been verified in laboratories. Single electrons can spin both clockwise and counterclockwise simultaneously. Atoms can occupy two energy levels at the same time. Even entire molecules have been placed into superposed states, their existence stretched between possibilities until measured. Schrödinger's cat, while hypothetical, embodies a real truth. Quantum mechanics allows nature to hold contradictions. The unsettling part lies in the act of measurement. Does opening the box force the cat into one state, collapsing the probabilities into fact? Or is reality branching, with one universe where the cat lives and another where it dies, each as real as the other? This is the heart of the paradox. The equations of quantum mechanics describe the superposition, but they do not tell us what becomes of it. Is the cat's fate suspended in possibility until witnessed, or does it divide existence into parallel outcomes beyond our perception? For scientists, the box becomes more than a story about animals. It is a metaphor for reality itself. The universe may be filled with unopened boxes at every scale, events poised between possibilities, worlds waiting for resolution. The paradox challenges the assumption that things must always have definite properties independent of observation. Instead, it suggests that reality is a question, with answers that emerge only when asked. Schrödinger never intended his cat to be taken literally. He offered it as a critique of how strange quantum theory seemed when applied to the familiar world. Yet the experiment has endured, not because of the cat, but because it captures the heart of quantum mystery in a single, unforgettable image. It shows how the smallest events can blur the line between potential and actuality, between what is and what could be. The unopened box is a mirror. It reflects the uncertainty woven into existence, the superpositions that lie hidden until revealed. It is a reminder that reality may not be fixed, but contingent, waiting for interaction to bring clarity. And as the journey continues, this paradox leads deeper still, toward the question of what it means for a wave function to collapse, and whether collapse itself is an illusion. At the center of quantum mechanics lies a question that has haunted physicists for nearly a century. What truly happens when a quantum system is measured? Before measurement, an electron or photon is not in one definite state, but in a superposition of many. Yet the instant observation occurs, the possibilities seem to vanish, leaving only a single outcome. This is known as the collapse of the wave function, a sudden shift from probabilities to fact. But what causes the collapse? Is it a real physical event, or an illusion created by limited perspective? The earliest and most widely taught answer is the Copenhagen interpretation. It holds that the wave function is not a physical thing, but a mathematical tool, a way of describing knowledge about the system. Collapse, in this view, is not a cosmic event, but the updating of information. Once a measurement is made, uncertainty disappears, not because reality has changed, but because the observer's knowledge has. Yet this explanation leaves many unsatisfied, for it seems to reduce reality itself to a matter of perspective. In contrast, the many worlds interpretation offers a bolder vision. Here, collapse never happens at all. Every quantum possibility is realized, but in different branches of the universe. If a photon has two possible paths, then the cosmos divides into two realities. One where the photon goes left, another where it goes right. In this picture, the universe is endlessly splitting, producing a vast multiverse in which every possibility is played out. The paradox is resolved, but at the cost of multiplying reality beyond comprehension. Another perspective comes from pilot wave theory, sometimes called Bohmian mechanics. It proposes that particles always have definite positions, guided by hidden waves that steer them through space. There is no collapse. Instead, unseen variables chart the course of events. This restores determinism, a comforting echo of classical physics, but requires accepting invisible forces that can never be directly observed. And then, there is the most unsettling possibility, that consciousness itself plays a role. Some interpretations suggest that awareness is the catalyst that collapses probabilities into facts. Until observed by a conscious mind, reality remains suspended in possibility. This view is controversial, and many physicists reject it outright, preferring explanations that avoid placing human awareness at the center of the cosmos. Yet the question lingers, for no experiment has fully banished it. Across all these interpretations, the collapse question remains unresolved. Experiments confirm the predictions of quantum theory with exquisite precision, yet they do not reveal what lies beneath. Physics can describe outcomes, but the meaning of collapse, whether real or illusory, singular or branching, continues to elude. This paradox is both limitation and invitation. It reminds that science has mapped the equations, but not the essence, traced the patterns, but not the underlying truth. In the collapse question lies the whisper that reality is deeper than measurement, more mysterious than mathematics. From here, the journey moves onward into the nature of time itself, where even cause and effect begin to unravel. Time, in ordinary life, feels simple. The past lies behind, the future waits ahead, and the present slips forward like a river. Clocks tick in rhythm, seasons turn, and memory confirms that moments arrive in order. Cause leads to effect, a match is struck, and then the flame appears. Yet in the quantum world, even this most familiar certainty begins to fray. Experiments hint that the order of events is not always fixed. Particles can behave as though outcomes ripple backward, reshaping what seemed to have already happened. In studies of quantum entanglement and delayed choice experiments, researchers have found that decisions made in the present can appear to influence results recorded in the past. A photon, for example, can seem to decide its path only after an observer chooses how to measure it, even if the measurement comes after the photon has already travelled. The chain of cause and effect, so fundamental to common sense, is tangled. The timeline bends, suggesting that sequence may not be as absolute as daily experience insists. This strangeness points toward a deeper possibility, that time itself may not be fundamental. Instead, it may be emergent, rising from more primitive layers of reality in the way temperature emerges from the motions of molecules. At the smallest scales, there may be no before and after, only a network of relations woven into patterns. Time, then, is not a line but a fabric, with threads looping and overlapping, their weave giving rise to the flow perceived at human scale. The arrow of time, so familiar in daily life, is tied to entropy, the tendency of systems to move from order into disorder. A cup falls, it shatters, and heat disperses. These changes never run backward. Yet entropy is not fundamental either. It emerges from the behavior of countless particles. At quantum scales, the arrow weakens. Processes may run forward and backward alike, their sequences indistinguishable. In this realm, time is no longer a strict current, but a sea in which motion can swirl in unexpected directions. This view unsettles assumptions carried for centuries. If time is emergent rather than fundamental, then the separation of past and future may be less real than it feels. Events may not be arranged along a single chain, but exist as part of a greater whole. The familiar rhythm of cause followed by effect becomes one perspective among many, valid at human scales but incomplete at deeper ones. To imagine time as a weave rather than a line is to see the universe differently. It is not a script written from beginning to end, but a tapestry where threads cross, fold, and sometimes blur. The quantum world invites the thought that the past and future are not as distinct as they seem, that the present may be less a point moving forward and more a window into a timeless fabric. From this mystery, the story flows naturally toward the dreams of hidden variables and determinism, visions of a reality that might lie beneath the shifting patterns. In the early years of quantum mechanics, its unpredictability left even its founders uneasy. Albert Einstein, who helped lay the very groundwork for the theory, could not accept a universe built on chance. To him, the idea that particles behaved randomly, that nature itself rolled dice, was incomplete. He believed there must be hidden variables, unseen mechanisms guiding the outcomes of quantum events, restoring order and determinism to a world that otherwise seemed ruled by probability. For decades, this hope shaped a quiet resistance to the mainstream view of quantum physics. If electrons and photons truly obeyed hidden rules, then their apparent randomness was only a reflection of ignorance, not of reality itself. Just as the shuffle of cards hides a predictable order, the quantum world might conceal a deeper logic waiting to be discovered. In this dream, reality was ultimately knowable, its mysteries temporary, its probabilities illusions that would dissolve once the hidden variables were found. But nature proved more elusive. In the 1960s, physicist John Bell formulated a theorem that set the stage for decisive tests. Bell showed that if hidden variables existed, they must obey certain mathematical inequalities. Experiments could then test whether particles followed hidden instructions, or whether they truly behaved in ways no deterministic theory could explain. What followed was a decades-long effort across laboratories around the world, firing entangled photons through detectors, closing loopholes one by one. The results, time and again, pointed in the same direction. The inequalities predicted by hidden variable theories were violated. Entangled particles did not carry pre-written scripts. Instead, they behaved in ways that defied classical logic. If hidden variables exist, they are not the simple mechanical guides Einstein imagined. They would have to be non-local, stretching across space instantaneously, stranger than anything in classical physics. In striving to preserve determinism, the dream revealed something even more unsettling, that reality itself may not be governed by hidden order, but by fundamental indeterminacy. Still, the dream of hidden variables lingers. It reflects a human longing for certainty, for a universe that can be fully understood if only the right keys are found. Determinism offers comfort, the belief that causes led to effects with unbroken continuity, that the cosmos is a vast clockwork whose gears can be mapped. Quantum mechanics challenges this comfort, replacing it with probabilities that never settle into absolutes until measured. Yet perhaps indeterminacy is not a flaw, but a feature. The universe, at its core, may be woven from possibility rather than certainty, its fabric one of openness rather than rigid law. This perspective transforms randomness from chaos into creativity, the source of novelty, the root of change. Without uncertainty, no new outcomes would ever arise. The hidden variable's dream may fade, but its shadow endures, a reminder of how deeply humanity yearns for clarity in a cosmos that resists it. From this paradox, the journey turns toward a different vision, one where reality itself may be more like information than matter, a code rather than a mechanism. When most imagine the foundations of reality, they picture particles, electrons, protons, quarks, all the tiny building blocks of matter. Yet some physicists argue that these are not the true substance of existence. Instead, beneath matter lies something more abstract: information. In this view, the universe is not made of things but of relationships, codes, and instructions, as though reality were written in symbols rather than forged from substance. The idea emerges from the peculiar nature of quantum states. A particle's position, spin, or momentum is not a fixed object, but a set of possible outcomes encoded in probabilities. These probabilities resemble data, carrying instructions for how the system behaves when measured. Information becomes the essence. Particles are its expression. It is not matter that defines the universe, but the rules that govern how matter appears, the hidden script beneath the play. Entropy itself, once described simply as disorder, is now understood as a measure of information. It tells how much is known or unknown about the state of a system. Black holes, the most extreme objects in the cosmos, deepen this mystery. Their surfaces seem to encode information about everything that falls into them, like a cosmic hard drive storing data in the fabric of space-time. Even energy and space may be emergent from information, woven from the bits and relations that underlie all phenomena. This perspective transforms the cosmos into something like a computation. The laws of physics resemble algorithms, rules that take inputs and generate outputs. Galaxies, stars, and atoms are the visible results of this continuous processing. The universe, vast and ancient, may be less like a machine of matter and more like an evolving program, endlessly running on the substrate of reality. In this sense, existence itself is a flow of information, a ceaseless calculation where knowledge and being intertwine. The idea does not necessarily mean simulation in the artificial sense, as though created by other beings. Instead, it suggests that the fabric of reality behaves as if it were informational at its base. Mathematics is not just a language to describe nature, it may be nature itself. The universe becomes a vast text written in equations and codes, unfolding word by word across the canvas of time. To see reality as information is to reimagine what it means for something to exist. A particle is no longer a solid thing, but a packet of instructions. A galaxy is no longer only stars and dust, but the manifestation of countless relations encoded in invisible data. Even consciousness in this framework might be understood as information processing, awareness born from the patterns of coded interactions. In this vision, physics becomes not only the study of forces and matter, but of meaning, the decoding of the universe's hidden script. Reality is not chaotic, but deeply structured, like an intricate program written in a language still being deciphered. From this perspective flows the next step in the journey. If reality is information, perhaps it is not singular at all, but branching endlessly, with every possibility written into the code of existence. Among the strangest answers to the puzzles of quantum mechanics lies an interpretation as vast as it is unsettling. It proposes that the wave function, that shimmering cloud of probabilities, never truly collapses at all. Instead, with every quantum event, reality itself divides. Each possibility is realized, but in different branches of the universe. Where the equations once seemed to demand a choice, this vision suggests that all choices unfold, not sequentially, but simultaneously, in an ever-branching multiverse. In this interpretation, when a particle has two possible paths, the universe splits. In one branch, the particle travels left. In another, it goes right. Both are real, both persist, and both continue to evolve with their own unfolding histories. Schrödinger's cat, suspended between life and death, is resolved not by collapse, but by division. One universe contains a living cat, another a lifeless one. Nothing is lost, everything is realized, endlessly proliferating across invisible frontiers. This idea, first proposed by Hugh Everett in the 1950s, is known as the many worlds interpretation. At first it was dismissed, too extravagant to be taken seriously. Yet over time, some physicists have come to see its elegance. It removes the need for mysterious collapse, leaving only the mathematics of the wave function unfolding deterministically across all branches. The paradox of measurement dissolves. but in its place arises a cosmos multiplied beyond comprehension, infinity upon infinity, each universe as real as this one. The implications are staggering. If many worlds is true, then every decision, every roll of the dice, every quantum fluctuation generates new universes. There is one where a photon chose the other path, one where a star formed differently, one where entire histories diverged. Within this infinity, versions of familiar worlds exist, some nearly identical, others unimaginably strange. Reality is no longer singular, but an endless ocean of parallel branches, each flowing silently beside the others, forever out of reach. And yet, the paradox remains. No experiment can prove or disprove this vision. The branches are hidden, inaccessible, never to interfere with one another. The mathematics allows them, but perception cannot confirm them. The multiverse expands invisibly, a silent backdrop against which our own branch unfolds. Whether it is truth or metaphor remains unresolved, but the idea lingers, elegant in its simplicity, terrifying in its scope. The many worlds interpretation offers more than scientific speculation. It is a mirror held up to human imagination. It whispers that this life may not be the only one, that every path not taken still unfolds somewhere, just beyond perception. It invites wonder and unease at a cosmos far richer than the senses can grasp. From this vision, the journey continues deeper, to a place where even emptiness is not what it seems, where the vacuum itself proves restless, alive with hidden potential. To the eye, empty space appears silent, still, and barren. It seems like nothingness, the absence of matter and motion, a void stretching endlessly between stars. But physics has revealed a truth far stranger. Emptiness is never truly empty. At the quantum level, the vacuum seethes with restless activity. Invisible particles flicker into being, then vanish again in fleeting instants, their existence brief but undeniable. This hidden dance is not a metaphor but a measurable fact, a reminder that what seems like silence is in fact a symphony too faint for ordinary senses to hear. Quantum field theory paints this picture with remarkable precision. According to its framework, every kind of particle is associated with a field that permeates all of space. Even when no particle is present, the field cannot be entirely still. It vibrates with zero-point energy. Fluctuations that never vanish, even at absolute zero. These fluctuations give rise to virtual particles, temporary sparks that appear and disappear, borrowing energy from the vacuum in perfect accordance with the laws of physics. The void, far from empty, is a storm in disguise. This restless foundation has consequences that shape the cosmos itself. The Casimir effect, observed in laboratories, reveals how two metal plates placed close together in a vacuum are gently pushed by the energy of these quantum fluctuations. In cosmology, the vacuum's latent energy plays an even greater role, linked to the mysterious force of dark energy that drives the expansion of the universe. What appears to be nothing exerts power, pressing outward on the very fabric of space-time, influencing the fate of galaxies and the horizon of cosmic time. The vacuum may also be the womb of universes. Theorists suggest that, under the right conditions, quantum fluctuations in this sea of potential could spark entire realities. Just as foam rises on the surface of a turbulent sea, so too could new universes bubble into being from the quantum vacuum, expanding and inflating into vast domains like our own. The void, then, is not absence but origin, a cauldron of possibility, the deepest reservoir of creation. To call it nothing is misleading. Nothingness would be the absence of fields, energy, and law itself. But the vacuum holds structure, rules, and restless vitality. It is, in truth, the most fundamental something, the canvas upon which the universe is painted, the stage that exists before any actor steps upon it. Without this quantum foundation, stars would not burn, matter would not endure, and the universe itself might not exist at all. From this perspective, emptiness transforms into fullness. Space between stars is not silent void but a living ocean, subtle and ceaseless. The vacuum reminds that beneath stillness lies motion, and beneath nothing lies the deepest kind of something. From here, the story turns toward gravity, the oldest force, still resisting quantum understanding, and perhaps the key to unlocking the next layer of reality's hidden design. Gravity was the first force humanity recognized. It was the pull that brought apples to the ground, the motion that carried the moon around Earth, the invisible thread binding planets to the sun. Centuries later, Einstein reimagined it, not as a force, but as the curvature of space-time itself, a bending of the cosmic fabric under the weight of matter and energy. His vision explained the dance of planets and the collapse of stars, uniting the heavens and the earth under one profound geometry. Yet, despite its elegance, gravity has resisted union with the other forces that rule the quantum world. Quantum mechanics describes the small with unmatched precision, the behavior of atoms, the sparks of light, the restless activity of fields. Relativity governs the large, galaxies, black holes, the expansion of the universe. Both theories work flawlessly in their realms, but together they clash. Where relativity demands smooth curves, quantum mechanics reveals restless fluctuations. At the edge of a black hole, where immense gravity meets quantum fields, the conflict grows sharp. Space and time themselves seem to tremble, and the need for a deeper theory becomes undeniable. Physicists search for this unification under the name of quantum gravity. String theory proposes that particles are not points but vibrating strings, their harmonies weaving both matter and space-time. Loop quantum gravity envisions space-time as granular, made of discrete loops and networks, tiny atoms of geometry. Other approaches suggest that space-time itself is not fundamental but emergent, rising from the entanglement of quantum states, as though the geometry of the universe is woven out of information. These ideas differ in form, but all whisper the same message. Reality may be less solid, less continuous than it appears. Hints arise in the most extreme places. At black hole horizons, paradoxes multiply. Information seems to vanish with falling matter, defying the laws of quantum theory, only to re-emerge in holographic principles that hint space-time may itself be a projection. In high-energy particle accelerators, collisions push physics towards scales where quantum gravity might reveal itself, though the signals remain elusive. Even the expansion of the universe, driven by dark energy, carries echoes of an unseen connection between gravity and the quantum vacuum. Despite decades of searching, no full picture has yet emerged. Quantum gravity remains a dream, a frontier not yet mapped, but within that dream lies possibility, the chance that reality itself will be revealed as something profoundly different. Perhaps space and time are not the fabric of existence, but threads spun from more fundamental relations. Perhaps geometry is an illusion, woven not from matter but from information, not from curves but from code. The paradox of gravity lingers, reminding science that even its strongest pillars are incomplete. To unify the large and the small is to step closer to the heart of reality itself. From this pursuit, the journey flows toward a still deeper mystery, the role of consciousness in the quantum world, and whether the act of awareness belongs inside the equations of physics themselves. Among the many paradoxes of quantum mechanics, none has stirred deeper wonder than the role of the observer. When a quantum system exists in superposition, hovering between possibilities, it remains unresolved until an observation is made. Only then does one outcome become fact. Some interpretations treat this collapse as a purely physical process, the interaction of systems reducing uncertainty to certainty. Yet others have dared to suggest something more radical, that awareness itself, the act of consciousness, is central to the transition from probability to reality. This view does not claim that the mind literally creates the universe, but it challenges the notion that consciousness is incidental. If the presence of an observer changes the outcome, then perhaps awareness is not outside the laws of physics, but woven into them. In this light, mind becomes more than a witness. It is a participant, entangled with the unfolding of reality, a shadow written into the equations even if undefined. The idea unsettled even great physicists. John von Neumann argued that measurement could not be fully explained until the observer was included. while Eugene Wigner speculated that consciousness might be essential to collapse the wave function. Though controversial, their reflections kept alive a question that refuses to fade. Is the mind simply recording what already is, or is it helping decide what becomes? Modern neuroscience has sought to place consciousness within the machinery of the brain, mapping its rhythms and processes. But even there, mysteries endure. Awareness does not reduce easily to electrical pulses and chemical flows. If quantum mechanics already blurs the boundary between observer and observed, then the enigma of consciousness only deepens the puzzle. The two mysteries intertwine, hinting at connections science has not yet unraveled. Experiments have not provided clear answers. Some argue that detectors alone suffice to collapse a wave function, whether or not a human mind is involved. Others point out that interpretation remains uncertain, that the chain of measurement always seems to leave open where, exactly, probabilities become facts. Does collapse occur in the instrument? In the brain? In awareness itself? The ambiguity persists, as though the question itself resists resolution. What emerges is a picture in which consciousness cannot be easily dismissed. It may not bend the cosmos to its will, but its presence alters how reality is described, demanding a place in the story of physics. Perhaps awareness is not an afterthought, rising from matter, but a fundamental aspect of existence alongside space, time, and energy. This possibility does not diminish science, but expands it. To consider mind within the fabric of reality is to acknowledge that the observer is never wholly separate from the observed. The cosmos, in this vision, is participatory, a dialogue between matter and awareness, probability and perception. The question remains open, profound, and unresolved. Is the mind only watching the play of the universe, or is it a co-author of the script? From here, the journey turns toward another provocative possibility, that if reality behaves like information, then perhaps all we see is but a shadow, a simulation woven from a deeper code. When physicists describe reality as information, the mind naturally drifts toward the idea of simulation. If the universe is structured like a code, if particles act like bits of data and quantum processes resemble calculations, then existence begins to look less like solid substance and more like a computation unfolding. The suggestion does not require creators outside the cosmos, nor programmers behind the curtain. It may simply mean that reality itself behaves as though it were a simulation-like system, written in the language of mathematics and governed by rules that resemble algorithms. The paradoxes of quantum mechanics feed this imagery. Superpositions resemble unresolved lines of code, instructions waiting to be executed. The collapse of the wave function resembles a program finalizing an output after input is received. Entanglement resembles a network where information flows instantly, no matter how far apart the nodes. Each of these strange behaviors, though deeply physical, mirrors processes familiar in computation. The mind reaches for the metaphor because it offers a frame, a way to picture the strangeness of a universe that does not behave like common experience. The notion of a simulated reality has been explored not only in philosophy but also in physics. Some researchers point to the discreteness of space and time, suggesting that if the universe has a smallest unit of distance or duration, it might resemble pixels on a screen or frames in a video. Others wonder if the speed of light acts like a processing limit, a maximum rate at which information can travel. Even the apparent randomness of quantum events might be read as the product of deeper informational rules hidden from view. And yet, to call reality a simulation can mislead, for it implies artifice, as though everything were manufactured by beings outside of it. The deeper insight is that simulation may not mean artificiality, but structure. The universe may not be fake, but it may behave in ways familiar to computation, because information itself is fundamental. Shadows of code may underlie the stars, not because they were programmed by others, but because the cosmos itself is inherently mathematical, its patterns unfolding like algorithms written into the heart of being. The imagery of shadow worlds, layered realities, and coded existence stirs both unease and wonder. It unsettles because it hints that what is seen, felt, and believed to be solid might only be surface, an interface to something deeper. But it inspires because it suggests that meaning lies beneath appearances, that the patterns of reality are not arbitrary, but profound. Whether or not the universe is a literal simulation, the metaphor reveals something true. Existence is structured, lawful and patterned, governed by relationships that can be read like text, like music, like code. To imagine life within such a system is not to diminish it, but to expand it. The stars remain radiant, the oceans vast, the mind mysterious, whether or not they are shadows of deeper rules. The simulation image reminds that what is taken as ultimate may only be a surface. From here, the story turns towards solidity itself, the question of whether matter is as stable as it feels, or whether even the most solid stone is a fleeting illusion of quantum motion. The world of human experience feels steady. A chair supports weight, a clock marks the passing of time, a stone can be held and passed from hand to hand. Buildings endure storms, mountains rise for ages, and the earth itself seems immovable. This sense of stability is so deeply ingrained that it becomes invisible, the background against which life unfolds. And yet, physics whispers a different truth. The solidity of daily life is not the whole story. Beneath every surface lies ceaseless motion, restless and unstill. Atoms, the supposed building blocks of matter, are mostly empty space. Their nuclei, dense with protons and neutrons, are surrounded by electrons that do not orbit like planets, but hover in clouds of probability. These electrons are never pinned down to exact locations. Instead, they flicker across regions, their presence uncertain until measured. Even the protons and neutrons within the nucleus are not solid, but composed of quarks bound by gluons, themselves fluctuating fields. The closer one looks, the less firm the ground becomes. Solidity dissolves into patterns of motion and possibility. Quantum mechanics deepens the paradox. Particles are never truly at rest. Even at absolute zero, the lowest temperature imaginable, they vibrate with zero-point energy. This restless activity cannot be extinguished, for uncertainty is built into the structure of the quantum world. The precise position and momentum of a particle can never be known at the same time, and so they are never fully fixed. What appears still at one scale is turbulent at another, a quiet storm hidden within the ordinary. The solidity experienced daily is an illusion of scale. At human dimensions, the dance of particles averages into stability. The countless motions blur into a surface that feels smooth, unchanging, dependable. A stone seems solid, not because it is still, but because the storm within it is too small and too fast to be felt. Solidity is the calm surface of quantum chaos, the illusion of permanence rising from impermanence. And yet, this illusion is not false comfort. It is the bridge that allows complex structures to exist, the foundation upon which life itself has evolved. Without stability at the macroscopic level, atoms could not bind, molecules could not persist, and the fragile order of living systems could not endure. Solidity may be an illusion, but it is also a gift, a stability born from the very uncertainty it conceals. The paradox humbles the mind. What feels most real is, at its foundations, more fluid and uncertain than appearances suggest. Matter is motion, form is fluctuation, and stability is a mask worn by chaos. The stone in the hand, the chair beneath the body, the clock on the wall, all are storms dressed as calm, order written upon ceaseless change. From here, the journey approaches its final question. If solidity itself is illusion, if time, matter, and observation all reveal paradoxes, then what is reality? The last step leads to the possibility that the quantum paradox itself may prove that reality, as it is experienced, is not what it seems, perhaps even a kind of shadow, a grand deception that conceals a deeper truth. The journey through quantum mysteries returns us to the simplest and most unsettling question: what truly is real? The very science that pulls back the veil of existence also seems to dissolve it. Particles act as waves until observed, as though awaiting acknowledgement before they choose a state. Entangled partners respond across galaxies as if distance were an illusion. Time itself bends and folds at the smallest scales, abandoning its steady march. Each paradox points not to a firm ground beneath appearances, but to shifting sand, a reality that trembles as it is touched. To call reality fake is not to dismiss the world as illusion in the trivial sense, but to recognize its deeper strangeness. The solidity of the everyday, the chair that holds, the stone that endures, is not wrong but incomplete. Beneath it lies uncertainty, probability, and entanglement, a structure less like a wall and more like a dream shared by countless participants. The quantum paradox suggests that reality is not fixed but contingent, not a rigid machine, but a fragile interplay between possibility and perception. This vision does not strip meaning from existence. On the contrary, it enriches it. If matter is not fundamental, if space and time are emergent, if even observation plays a role in shaping outcomes, then life itself is woven into the fabric of creation more intimately than once believed. The paradox reminds us that the cosmos is not merely an external stage, but a dialogue between what is and what can be. To live within it is to dwell in mystery, to be part of the unfolding rather than apart from it. Some interpretations reach for the metaphor of simulation, describing reality as informational, coded, structured like a vast program. Others lean toward multiverses, where every possibility finds expression somewhere, splitting reality into infinite branches. Still others see in the paradox an invitation to humility, to admit that the tools of thought may never fully capture the whole. Whether the world is fake or real becomes less important than recognizing that its appearance is partial, that behind every certainty lies uncertainty, and beneath every answer a deeper question. What endures is not deception but wonder. The paradox does not negate existence. The stars still shine, the oceans still move, breath still fills the lungs, but it reframes them, showing that what seems simple is layered with mystery. Reality may be less a finished structure than an open process, a possibility collapsing into the present moment, endlessly renewed. The universe itself becomes the grandest paradox, both real and unreal, both fixed and fluid, both solid and dreamlike. The final whisper is perspective. To call reality fake is only to admit that it is not what it seems. It is stranger, subtler, more fragile, and more beautiful than ordinary sight can know. Science, in revealing its paradoxes, does not end the story but opens it wider, offering not certainty but awe. And in that awe lies a quiet truth. Perhaps the universe is not something observed from the outside, but something lived from within. The unfolding of a shared dream that continues moment by moment into eternity.